Imagine a time before stars, before galaxies, before even the faintest glow flickered in the endless darkness. The universe was a black canvas, silent and empty, until something extraordinary happened. The very first light pierced through the void, a cosmic spark that ignited everything we know. That moment, hidden in the depths of time, holds secrets that scientists have been racing to uncover for decades. And today, we're diving deep into the mystery of that primordial glow, the universe's first light. Picture this, a faint, ghostly radiation lingering in every corner of space, a cosmic whisper from the dawn of time. It's called the cosmic microwave background, and it's the oldest light we can detect, a remnant of that initial flash that transformed the universe forever. But how did light even begin? What cosmic forces conspired to break the darkness? The answers aren't just buried in equations or telescopes, they're woven into the fabric of reality itself. And the theories, they're as wild and wondrous as the cosmos. From quantum fluctuations to collisions of unimaginable energy, the story of light's birth is anything but simple. This isn't just a tale for astrophysicists, it's a journey for anyone who's ever looked up at the night sky and wondered, how did it all begin? Over the next 30 theories, we'll explore the boldest, most mind-bending ideas about that first flicker of light. Some will challenge everything you thought you knew. Others might feel like science fiction until you realize they're backed by cutting-edge research. So whether you're a space enthusiast or just love a good cosmic mystery, buckle up. We're about to rewind time to the very edge of existence, to the moment light itself was born. And trust me, the story is even stranger than you think. Let's start with the most widely accepted explanation, the moment light first escaped into the universe. Picture the Big Bang not as an explosion in space, but as the rapid expansion of space itself. In those first unimaginably hot moments, the universe was a seething soup of particles, protons, electrons, and photons, all packed so tightly that light couldn't travel more than a fraction of an inch before being absorbed or scattered. It was like being trapped in an endless cosmic fog. Then, about 380,000 years after the Big Bang, something pivotal happened. The universe had cooled enough for electrons to finally latch onto protons, forming the first atoms of hydrogen. This event, called recombination, was light's great escape. Suddenly, photons, the particles of light, could travel freely for the first time. No longer bouncing endlessly in the particle soup, they raced outward in every direction. That flash of liberation is what we now detect as the cosmic microwave background, the afterglow of the Big Bang itself. But here's the twist, that first light wasn't the fiery blaze we might imagine. The universe was still relatively cool by cosmic standards, around 3,000 degrees Celsius, hot enough to glow, but not with the visible light we see today. Instead, it was a dim red haze stretched over billions of years into the microwave radiation we now observe. And yet, that faint echo holds the blueprint of the early universe, a snapshot of its structure before stars or galaxies even existed. Scientists have spent decades decoding its subtle patterns, uncovering clues about how everything from the tiniest atoms to the largest superclusters began. This theory isn't just a neat origin story. It's backed by precise measurements like the cosmic microwave background's near-perfect uniformity, with tiny fluctuations that eventually seeded galaxies. But as solid as the Big Bang flash theory seems, it's just the beginning of our journey, because while recombination explains how light broke free, it doesn't answer everything. What triggered the Big Bang itself? Could there have been light even earlier, lost to time? The deeper we dig, the stranger the theories get. But what if that first light didn't come from the Big Bang's afterglow at all? There's another cosmic turning point where darkness truly surrendered to light, a moment astronomers call the end of the cosmic dark ages. Think of it like this: After that initial flash of the cosmic microwave background, the universe plunged back into shadow for millions of years. The hydrogen atoms formed during recombination absorbed any stray light, leaving space pitch black once more. No stars, no galaxies, just an endless sea of cold, neutral gas stretching across the expanding cosmos. Then, somewhere in that darkness, a spark flickered, not from the remains of the Big Bang, but from something entirely new, the birth of the very first stars. These weren't like the stars we know today. They were monsters hundreds of times more massive than our sun, burning furiously hot and dying young in spectacular explosions. Their ultraviolet radiation blasted through the surrounding hydrogen gas, stripping electrons from atoms in a process called reionization. It was like someone flicking on a cosmic light switch, ending the Dark Ages and flooding the universe with starlight for the first time. Here's where it gets even more fascinating. These first stars didn't just light up the cosmos, they changed its very chemistry. In their cores, they forged the first heavy elements like carbon and oxygen, the building blocks of planets and life. When they exploded as supernovae, they scattered these elements across space, seeding future generations of stars and the light from those violent deaths. It was so powerful that some scientists believe it might have triggered the formation of the first galaxies. The evidence for this theory comes from some of the most distant objects we've ever observed. Telescopes like Hubble and James Webb have spotted galaxies so far away that their light has traveled nearly 13 billion years to reach us. In their faint glow, we see hints of this cosmic dawn, the moment starlight began sculpting the universe as we know it. But mysteries remain. Were these the very first stars or just the earliest we can see? Could there have been even older, fainter sources of light lost to time? What's undeniable is that this transition marked a revolution. The Dark Ages weren't just an empty void, they were the universe's quiet incubation period, a necessary pause before the fireworks began. And when they ended, everything changed. Light became more than just a fleeting flash. It became the sculptor of galaxies, the engine of chemistry, the herald of everything to come. The cosmic microwave background might be the oldest light we can detect, but the starlight that broke the Dark Ages, that's when the universe truly woke up. Now let's venture into one of the more daring theories where light's origins might trace back to the universe's darkest objects, primordial black holes. Imagine black holes not as the destructive monsters we often picture, but as cosmic midwives helping to deliver the first light into existence. These aren't the black holes formed from collapsing stars. These are relics from the universe's first moments, smaller than an atom yet heavier than a mountain, born in the chaos of the Big Bang itself. Here's how it might have worked. In those early instants, the universe was so dense that random fluctuations in energy could have crumpled pockets of space into ultra-tiny black holes. And according to Stephen Hawking's groundbreaking work, black holes aren't entirely black. They emit a faint glow, now called Hawking radiation, as particles slowly leak out from their edges. For primordial black holes, this process could have been explosive. The smallest ones would have evaporated in a flash of energy, releasing bursts of radiation, potentially the universe's first light. But the story doesn't end there. Some theorists suggest these black holes might have also acted as seeds for the first stars. Their immense gravity could have pulled in surrounding gas, creating hotspots that ignited nuclear fusion. Picture it, a tiny black hole, barely visible, serving as the spark for a stellar firestorm. The light from those first stars wouldn't just illuminate the cosmos, it would redefine it, carving out the structures that eventually became galaxies. Evidence, it's tantalizing but indirect. Some astronomers point to mysterious gaps in the cosmic microwave background, tiny cold spots that could be scars from primordial black holes evaporating long ago. Others hunt for unexplained gamma-ray bursts, flashes of energy that might be the last cries of these ancient objects. If we could detect even one primordial black hole today, it would rewrite our understanding of light's origins. Of course, this theory isn't without its skeptics. Critics argue that Hawking radiation from such small black holes would be too faint to compete with other light sources. And if these objects were so common, why haven't we found definitive proof? Yet that's the beauty of this idea. It forces us to rethink the relationship between darkness and light. Maybe the universe's first glow didn't come from a fiery burst, but from the quiet fade of something unimaginably dense. What's striking is how this twists our usual narrative. We often see black holes as the end of light, the ultimate cosmic voids. But if this theory holds, they might also have been its beginning. It's a reminder that in the early universe, the rules were different, and the most surprising actors could have played the hero. And as we dig deeper into the cosmos's secrets, we're left wondering how many other unseen forces shaped the dawn of light. Deep in the quantum soup of the early universe, reality itself was flickering in and out of existence. Picture a space so turbulent that particles and energy popped into being for mere fractions of a second before vanishing again. A cosmic dance of creation and destruction on the smallest scales imaginable. These weren't random glitches in the fabric of reality. They were quantum fluctuations, tiny ripples in the energy field that filled the infant cosmos. And according to some physicists, these fleeting disturbances might hold the key to the universe's first light. Here's how it could have happened. In those first moments after the Big Bang, the universe wasn't just expanding. It was a seething, chaotic arena where gravitational waves and energy fields clashed violently. Quantum fluctuations, normally too small to notice, were stretched to enormous sizes as space itself ballooned outward. These ripples carried subtle differences in density, some regions slightly hotter, others cooler, and as the universe cooled, those variations could have triggered localized bursts of energy. Think of it like bubbles forming in boiling water, except these bubbles were pockets of concentrated radiation that, when they popped, released the earliest photons. The real magic happened as the cosmos continued to expand and cool. Those initial quantum ripples didn't just fade away. They froze into place, becoming the seeds for the cosmic microwave background's faint temperature variations. Today, we see those ancient fingerprints imprinted across the entire sky, a telltale sign of the quantum origins of light. Some researchers even suggest that without these fluctuations, the universe might have remained a featureless void, never giving rise to the stars and galaxies we know. But here's where the theory gets even wilder. Quantum effects aren't just confined to the microscopic world. In the extreme conditions of the early universe, they may have played a role in breaking the symmetry between matter and antimatter, allowing light to propagate freely. There's also the tantalizing possibility that some of those early photons weren't just passive emissions. They could have been entangled, linked across vast distances in ways we're only beginning to understand. While this idea might sound like science fiction, it's grounded in solid physics. Quantum field theory predicts these fluctuations, and observations of the cosmic microwave background match the patterns we'd expect from such microscopic disturbances. The challenge is proving that these tiny ripples directly led to visible light. Some simulations suggest that as the universe expanded, the energy from those fluctuations could have cascaded into larger waves, eventually igniting the first luminous phenomena. What's fascinating is how this reshapes our view of cosmic dawn. Light didn't just switch on like a lamp, it bubbled up from the quantum foam, a slow simmer before the universe's grand illumination. And if we're right, those same fluctuations didn't just create light, they set the stage for everything that followed. Without them, the cosmos might still be a silent, unchanging expanse. Instead, we have a universe ablaze with stars, galaxies, and the echoes of its own improbable birth, yet mysteries linger. Were these fluctuations truly random, or did some deeper principle guide them? Could they explain why certain regions of space seem to glow more intensely than others? And if light emerged from these quantum tremors, what does that mean for the nature of reality itself? Every answer pulls us deeper into the puzzle of how something as intangible as a quantum flicker could ignite the brilliance of the cosmos. Hidden in the fabric of the universe, there might be cracks, ancient scars from the Big Bang so strange they defy ordinary physics. These are cosmic strings, hypothetical threads thinner than an atom but stretching across the entire cosmos, vibrating with unimaginable energy. Picture them like flaws in a frozen lake where the ice cracked as it cooled, except here the ice is space-time itself. And according to one radical theory, these strings could have been cosmic matchsticks, sparking the universe's first light through sheer friction. Here's how it might have worked. In the early universe, cosmic strings wouldn't have been static. They'd have writhed and snapped, crossing one another like tangled guitar strings. Every time two strings collided or a loop of one broke apart, the energy released could have been catastrophic, enough to tear open miniature black holes or unleash torrents of radiation. But some physicists argue the real fireworks came from something subtler, the strings simply vibrating against the dense particle soup around them. As they moved, their immense gravitational pull would have dragged matter along, compressing it until it glowed. Think of it like rubbing your hands together on a freezing day, except these hands were cosmic filaments heating the universe's first plasma to billions of degrees. The echoes of this process might still be visible today. If strings existed, their violent motions could have left faint imprints in the cosmic microwave background, distinctive jagged patterns or sudden temperature spikes. Some researchers even suggest that the most powerful gamma-ray bursts ever recorded could be the death throes of cosmic strings snapping after billions of years. It's a tantalizing lead, though not without controversy. Critics point out that no definitive evidence of strings has ever been found, and simulations show their light signatures might blend into other cosmic noise. Yet the idea captivates because it turns our understanding of light's origins upside down. Instead of emerging gently from cooling plasma or exploding stars, the first photons might have been born from spacetime itself unraveling. And if strings are real, they're not just relics, they could still be out there, humming in the dark, weaving the cosmos into shapes we've yet to imagine. Maybe the universe's oldest light wasn't a single event, but a symphony of cracks and shudders in the very framework of reality. What's striking is how this theory blurs the line between structure and energy. Cosmic strings aren't just objects, they're defects in the universe's geometry, flaws so profound they could generate light simply by existing. It raises a haunting question. If spacetime can flicker with radiation when stressed, what other hidden phenomena might be lighting up the cosmos? The search for answers isn't just about the past, it's about uncovering the invisible architecture of everything. Long before the delicate balance of elements we see in stars today, the universe forged its first stellar giants in an entirely different crucible. These were the population 3 stars, mythic beasts composed of nothing but pristine hydrogen and helium, the only elements that existed after the Big Bang. Without heavier elements to regulate their growth, they ballooned to sizes we can barely comprehend, some weighing 100 times more than our Sun. And when they finally ignited, their light didn't just illuminate the cosmos, it transformed it forever. The birth of these stars was unlike anything happening now. Today, star formation is a relatively orderly process. Gas clouds fragment into smaller clumps, dust helps cool them, and gravity slowly pulls them together. But in that primordial era, there was no dust, no carbon, no oxygen to radiate heat away. The only force at work was raw gravity pulling hydrogen together until it reached unimaginable densities. Simulations show these first stars likely formed in near isolation, growing unchecked until their cores became so hot and dense that nuclear fusion erupted with terrifying intensity. The light they emitted wasn't the familiar white-yellow of our Sun. It was a searing ultraviolet blaze, powerful enough to rip electrons from surrounding hydrogen atoms across vast distances. What made these stars truly extraordinary wasn't just their size, but their life cycle. burning at such extreme temperatures they exhausted their fuel in just a few million years, a cosmic blink compared to the Sun's 10 billion-year lifespan. Their deaths were equally spectacular. Instead of fading quietly, they likely collapsed into massive black holes or exploded as hypernovae, eruptions so violent they briefly outshone entire galaxies. These cataclysms forged the first heavy elements: carbon, oxygen, silicon, scattering them into space where they'd eventually form planets and life. That starlight didn't just end the cosmic dark ages, it created the very ingredients needed for everything that followed. The hunt for population 3 stars remains one of astronomy's greatest challenges. By rights, none should still exist. Their short lifespans mean the last one died billions of years ago. But with telescopes like James Webb, we're peering back to the era when their light first pierced the darkness. Some researchers believe we might spot their distinctive ultraviolet signatures in the most distant galaxies. Others look for their chemical footprints, patches of space strangely devoid of heavy elements, possible graveyards where these titans once blazed. What's astonishing is how much hinged on these ephemeral monsters. Without their extreme radiation, the universe might have remained a cold, neutral sea of hydrogen. Without their explosive deaths, there'd be no planets, no chemistry beyond the simplest atoms. Their light didn't just break the darkness, it set in motion the chain of events that led to stars like our Sun, to Earth, and ultimately to us. Every element in your body, every photon warming your skin, traces back to those first fleeting giants. They were the universe's first true artists, painting the cosmos with light and chemistry where before there was only void, yet mysteries persist. Were all population 3 stars behemoths, or did some form smaller? Did they shine alone or in clusters, and could their remnants, those ancient black holes, still be lurking unseen in today's galaxies? Each question reminds us how different the early universe was from the orderly cosmos we see now. Back then, stars weren't just points of light. They were cosmic revolutionaries, rewriting the rules of existence with every furious blaze. Dark matter has always been the universe's most frustrating ghost, undeniable in its gravitational effects, yet invisible to every telescope we've built. But what if this mysterious substance didn't just lurk in the shadows? What if, in the earliest moments of the cosmos, dark matter was the spark that ignited the first light? This theory hinges on a process as violent as it is elegant: annihilation. Picture 2 dark matter particles hurtling through the primordial darkness, colliding with such force that they obliterate each other in a flash of energy. According to some physicists, those fleeting moments of destruction could have flooded the young universe with photons, lighting the darkness long before stars took center stage. The math behind this idea is compelling. Most dark matter models suggest these particles are their own antimatter counterparts, meaning when 2 meet, they don't just bounce off each other but vanish entirely, converting their mass into pure energy. In today's universe, these events would be rare, with dark matter spread too thin for frequent collisions. But in the ultra-dense early cosmos, annihilations might have been constant, a fireworks show of particle destruction bathing everything in radiation. Some calculations suggest this process could have outshone even the Big Bang's afterglow for brief, brilliant moments. But here's where it gets even stranger. The light from dark matter wouldn't have looked like sunlight or starlight. Depending on the particles involved, it might have manifested as X-rays or gamma rays, invisible to human eyes but powerful enough to ionize surrounding hydrogen, stripping electrons from atoms and reshaping the cosmic landscape. There's even a controversial idea that these high-energy photons could have kick-started the formation of the first molecules, acting as cosmic catalysts in a universe still learning how to build complexity. Evidence for this theory is tantalizingly indirect. Astronomers have spotted unexplained patches of excess gamma radiation in distant galaxy clusters, precisely the places where dark matter should be densest. Then there's the cosmic infrared background, a faint glow across the sky that doesn't quite match predictions from known light sources. Could this be the faded fingerprint of ancient dark matter annihilation? The challenge is separating these signals from other phenomena, like supermassive black holes or neutron star collisions. What makes this idea so revolutionary isn't just the physics, it's the philosophical shift. We're used to thinking of dark matter as passive scaffolding, quietly shaping galaxies through gravity alone. But if annihilation light is real, dark matter wasn't just part of the universe's structure, it was an active participant in its illumination. The darkest stuff in existence might have helped create the first light, a poetic twist that would make even the most skeptical cosmologist pause. Of course, major questions remain. Why didn't all the dark matter annihilate itself away in those early moments? What stopped the process, leaving enough behind to dominate the cosmos today? Each mystery pulls us deeper into the enigma of dark matter's true nature. And if we're right, every photon lighting the night sky, from distant quasars to the glow of your screen, might owe its existence in part to the invisible particles we're still struggling to understand. The universe's first light could have been a shadow's final act, a fleeting transformation from darkness into brilliance that set the stage for everything to come. Before stars, before galaxies, before even the first atoms, there was a moment when the universe expanded faster than light itself. This was cosmic inflation, a split-second frenzy where space stretched 100 trillion times over in less than a blink. And while we often picture this epoch as a silent, empty leap, some theorists believe it wasn't empty at all. Hidden in that hyper-expansion might have been the seeds of the universe's first light. Photons born not from fire or collision, but from space itself tearing apart at the seams. Here's the paradox. Inflation is supposed to have left the universe cold and dark, stretched so thin that all energy was diluted to nearly nothing. But quantum physics tells us empty space is never truly empty. At the tiniest scales, virtual particles flicker in and out of existence, borrowing energy from the void before vanishing again. During inflation, these fleeting fluctuations were stretched to cosmic proportions, frozen into the fabric of space-time like wrinkles in an expanding balloon. And when inflation abruptly ended, all that pent-up energy had to go somewhere. Some calculations suggest it reheated the universe in a violent burst, converting that quantum static into real particles, including photons. These wouldn't have been ordinary photons. Inflation's extreme conditions could have birthed light with bizarre properties, super high-frequency waves that redshifted over billions of years into the gentle glow we now see as the cosmic microwave background. Others might have carried imprints of the inflationary field itself, remnants of the force that drove the universe's exponential growth. If we could decode those signals, it'd be like finding a recording of the Big Bang's first notes. Clues might already be hiding in plain sight. The cosmic microwave background's temperature fluctuations, those faint blotches that map the early universe's density, could be inflation's fingerprints. Some patterns in those patches, like unexpected swirls in polarization data, might reveal how inflationary photons interacted with matter. There's even a hunt for primordial gravitational waves, ripples in spacetime from inflation that could have left a distinct imprint on light's oldest fossils. What's mind-bending is how this reshapes light's origin story. Instead of emerging from a hot plasma or dying stars, the first photons might have been a side effect of space itself unraveling. The energy driving cosmic expansion didn't just vanish. It transformed, echoing through the ages as the light we now use to study the cosmos. And if we're right, every telescope peering into the night sky is catching the last whispers of inflation itself, stretched across 14 billion years but still telling us how it all began. Yet mysteries linger. Why did inflation stop so abruptly? What determined how much energy converted into light versus matter? And if inflation's photons still permeate space, could they hold secrets about dimensions beyond our own? Each question leads deeper into the quantum roots of reality, where light wasn't just a product of the universe's birth, but a witness to its most explosive growing pains. Imagine the universe just moments after the Big Bang, not as a tranquil expanse, but as a superheated ocean of charged particles roiling like a stormy sea. This wasn't just any plasma, it was a frenzied soup of electrons and protons so dense that light couldn't travel freely. Yet within that chaos, something remarkable was happening. Tiny ripples of energy, like waves crashing in an invisible ocean, might have given birth to the universe's first detectable light. These weren't random flickers, they were plasma oscillations, rhythmic surges of charged particles that could have generated electromagnetic waves powerful enough to pierce the cosmic fog. Here's how it works. In that primordial plasma, electrons and protons weren't sitting still, they were constantly jostling, repelling, and attracting one another. When a group of electrons got pushed together by some fluctuation, their negative charges would create a force pushing them apart again. This back and forth created waves of compression and rarefaction, much like sound waves traveling through air. But in a plasma, these oscillations don't just produce sound, they generate electromagnetic fields. As the charged particles vibrated, they could have emitted photons, the fundamental particles of light. It's like shaking a bell, except instead of sound, the vibrations produced the first glimmers of illumination in the cosmos. The scale of these oscillations was staggering. Some models suggest the waves could have spanned entire regions of the early universe, with frequencies millions of times higher than anything we observe today. And the light they emitted wouldn't have been the gentle glow we associate with stars, it would have been an intense burst of radiation, possibly even X-rays or gamma rays. Over time, as the universe expanded and cooled, those high-energy photons would have stretched into longer wavelengths, eventually becoming part of the cosmic microwave background we detect now. But here's the twist. These plasma oscillations didn't just create light, they might have shaped the very structure of the universe. The waves could have created subtle variations in density, regions where matter clumped slightly more or less, seeding the formation of the first galaxies. Some researchers even speculate that certain anomalies in the cosmic microwave background, small, unexplained hot or cold spots, could be echoes of these primordial plasma waves frozen in time like a cosmic fingerprint. Evidence for this theory is still emerging. Advanced simulations of the early universe show that plasma oscillations could indeed produce detectable electromagnetic waves under the right conditions. And observations from space telescopes have revealed faint, large-scale patterns in the distribution of matter that align with what these oscillations might leave behind. But proving definitively that these waves were responsible for the first light remains a challenge. The signals are incredibly faint, buried under billions of years of cosmic noise. What's fascinating is how this theory turns our understanding of light's origins on its head. Instead of emerging from a single, cataclysmic event like the Big Bang or the birth of stars, light might have arisen from countless tiny vibrations, a chorus of charged particles singing the universe into illumination. It's a reminder that even in the most chaotic environments, order can emerge, and sometimes that order shines, yet mysteries linger. Were these oscillations uniform, or did they vary wildly across different regions of the early universe? Could they explain why some parts of space seem to glow more intensely than others? And if plasma oscillations really did generate the first light, what does that tell us about the fundamental nature of energy and matter? Every answer pulls us deeper into the story of how darkness first gave way to light, not with a bang but with a vibration. Neutrinos are the universe's most elusive particles, so light they barely interact with matter, streaming through planets and stars like ghosts. But what if these shadowy particles held the key to the universe's first light? There's a radical idea in astrophysics suggesting that in the extreme conditions of the early cosmos, neutrinos might not have been stable. Instead, they could have decayed into something far more luminous, photons. This process, called radiative decay, could have flooded the infant universe with light long before stars ever flickered to life. Picture a universe just seconds old, so dense and hot that neutrinos outnumbered protons by billions to one. Today, neutrinos zip through space almost eternally, rarely changing or interacting. But back then, the rules were different. Some theories propose that neutrinos might have had slightly more mass in the early universe or interacted with undiscovered particles that triggered their decay. As these neutrinos broke apart, they'd have released energy in the form of photons, particles of light. Unlike the violent brilliance of stars or the afterglow of the Big Bang, this light would have emerged softly, a silent glow permeating the cosmos from every direction. The implications are staggering. If even a fraction of the universe's neutrinos decayed this way, they could have produced enough light to ionize hydrogen gas, ending the cosmic dark ages earlier than we thought. Some calculations suggest this neutrino decay light might have left subtle fingerprints in the cosmic microwave background, peculiar polarization patterns, or unexpected temperature variations that don't align with standard Big Bang predictions. There's even a chance it could explain certain anomalies in the distribution of matter we see today, as the gentle pressure of this early light might have pushed gas into the filaments and voids we observe in the large-scale structure of the cosmos. Of course, proving this theory is a monumental challenge. Neutrinos are notoriously difficult to study. Trillions pass through your body every second without a trace. To catch one decaying would require detectors of unimaginable sensitivity, yet there are tantalizing hints. Some astrophysicists point to unexplained excesses of diffuse light in deep space observations, faint glows that don't seem tied to any known source. Others note that certain neutrino experiments have recorded anomalies in the particle's behavior that could, theoretically, hint at undiscovered decay pathways. What makes this idea so compelling is how it flips our understanding of cosmic lighting on its head. We're used to thinking of light as coming from stars, explosions, or quantum fluctuations, active energetic processes. But if neutrinos decayed into photons, it would mean the universe's first light came from something fundamentally passive, a quiet transformation of the most inert particles in existence. It's a reminder that in the early cosmos, even the slightest shifts in particle physics could rewrite the story of illumination. The bigger question lingers: if neutrinos did decay, what stopped them? Why do we still detect them today? Some theorists suggest only a certain type of neutrino, perhaps a heavier, now extinct variant, underwent this process, leaving the lighter ones we observe now. Others propose that decay rates slowed as the universe expanded, freezing the remaining neutrinos in place. Every possibility opens new doors to understanding these enigmatic particles and their role in shaping the cosmos. Perhaps the most poetic aspect of this theory is the idea that light didn't just come from the universe's chaos, it emerged from its silence. While black holes collided and stars ignited, neutrinos might have been the unseen hand quietly painting the cosmos with their fading glow. And if we're right, the universe's first light wasn't a shout, but a whisper one we're only now learning how to hear. Deep in the fiery plasma of the early universe, sound waves raced outward at half the speed of light, not through air, but through an ultra-dense soup of particles so packed together they behaved like a fluid. These weren't ordinary sound waves, they were baryon acoustic oscillations, pressure pulses that rolled through the infant cosmos like cosmic tsunamis. And their aftermath, it might hold the key to why light isn't randomly scattered across space but clustered in a vast, intricate web of galaxies and voids. Imagine the universe just 400,000 years after the Big Bang, still a seething ocean of protons and electrons, but cooling rapidly. Gravity had started pulling matter together, but there was a counterforce, radiation pressure from photons. When matter clumped slightly in one region, photons pushed back, creating a back-and-forth battle between compression and expansion. The result was spherical pressure waves rippling outward, each crest leaving behind a shell of matter like rings in a pond. These frozen ripples became cosmic assembly lines, determining where galaxies would later form. The genius of this process lies in the scale, because these waves traveled at a fixed speed before the universe cooled enough to freeze them in place. They left a predictable pattern, a preferred distance between galaxy clusters that astronomers call the cosmic ruler. Today, we can measure this. Surveys of millions of galaxies reveal they're slightly more likely to be separated by about 500 million light-years, an echo of those primordial sound waves. But here's where light enters the story. The same waves that shaped matter distribution also influenced where hot, glowing gas collected. When the universe became transparent and light finally broke free, regions where baryon waves had piled up matter shone brighter, packed with more ionized hydrogen to emit photons. This created a cosmic checkerboard, bright knots where waves peaked and darker voids where they troughs. The cosmic microwave background's temperature variations. Those are essentially snapshots of these waves caught mid-oscillation, like freezing a drumhead's vibration in time. What's mesmerizing is how enduring this fingerprint turned out to be. Those ancient sound waves didn't just fade, they set the template for all structure in the universe. The galaxies we see today, the vast filaments of the cosmic web, even the voids between them, all trace back to those pressure pulses in the primordial plasma. And the light we detect from distant quasars, its absorption lines still carry subtle hints of those waves, as if the universe never forgot its first rhythm. Yet mysteries endure. Why do some galaxy clusters seem slightly offset from where the waves predict? Could dark matter have altered the oscillations in ways we're only starting to understand? And if we could hear those sound waves today, stretched across 14 billion years of expansion, would they resemble a deep cosmic hum or a chorus of fading echoes? Every answer pulls us closer to understanding how order emerged from chaos, not just in the distribution of matter, but in the very light that lets us see it. Among the countless particles we've discovered, there might lurk others strange, undiscovered bits of matter that existed only in the universe's first moments. These aren't just theoretical curiosities, they could be the missing architects of light's origin. According to some physicists, certain exotic particles, ones not found in our current standard model, might have briefly flickered into existence during the Big Bang's extreme conditions, only to decay in a flash of radiation. Their deaths could have been the universe's first sunrise. Take the hypothetical action, for example. Predicted to solve mysteries in quantum physics, this lightweight particle might have been abundant in the early cosmos. Under intense heat and pressure, axions could have transformed into photons through a process called the Primordial effect. It's like a cosmic alchemy trick, turning invisible, weakly interacting particles into bursts of light. Other candidates, like sterile neutrinos or WIMP, weakly interacting massive particles, might have undergone similar transformations, their decays flooding the universe with photons long before stars ignited. The beauty of this idea lies in its testability. If exotic particles decayed into light, they'd leave distinct signatures in the cosmic microwave background, subtle twists in polarization or unexplained spikes in certain frequencies. Some researchers even suggest that anomalies in deep space gamma-ray observations could be the faint echoes of these particles' final moments. There's also the tantalizing possibility that these decays didn't just produce light passively. They might have triggered chain reactions, ionizing surrounding gas and jump-starting the formation of the first structures in the cosmos. Critics argue that inventing new particles to explain light's origins feels like a shortcut, but proponents counter that the standard model is incomplete. It can't explain dark matter or gravity's quantum behavior. If exotic particles exist, their role in lighting the early universe would solve multiple puzzles at once. The hunt is already underway, with experiments like CERN Atlas detector searching for action-like signals, while telescopes scour the sky for the telltale glow of decaying relics. What's fascinating is how this reshapes our view of cosmic dawn. light might not have emerged from something we'd recognize as matter today. Instead, it could have been a farewell gift from particles that vanished almost as quickly as they appeared, ghosts in the quantum machine, leaving behind the glow that now fills the cosmos. If we're right, every photon we see carries traces of a shadow universe, one we're only beginning to imagine. What if the light we see from the early universe isn't real, at least not in the way we think? Imagine gazing at a starry sky only to realize those pinpricks of light are projections, like shadows cast on a cave wall. This isn't science fiction. It's the holographic principle, a radical theory suggesting our three-dimensional cosmos, with all its galaxies and light, might be encoded on a two-dimensional surface at the edge of spacetime. And if that's true, the universe's first light could be nothing more than a cosmic illusion, a shimmering mirage born from information flickering on the boundary of reality itself. The idea builds on a startling discovery about black holes. In the 1970s, physicist Jacob Bekenstein calculated that the entropy, or disorder, of a black hole isn't proportional to its volume but to its surface area. This hinted that all the information inside a black hole might somehow be stored on its event horizon, like a celestial hard drive. Decades later, string theorists like Leonard Susskind took this further, proposing that the entire universe could work the same way. Our reality, with its stars, planets, and even the ancient glow of the cosmic microwave background, might be a hologram, a three-dimensional projection of data written on a distant, flat surface. So how could this explain the first light? Picture the early universe not as a volume of space, but as a seething, two-dimensional sheet of quantum information. Fluctuations in that data would manifest as energy in our three-dimensional world, including photons. The light we detect from the cosmic dawn wouldn't be emitted by distant objects, but decoded from patterns on the universe's edge, translated into the illusion of illumination. It's like watching a movie projected on a screen, except the screen is the boundary of existence, and the film is reality itself. Evidence for this is speculative but tantalizing. The cosmic microwave background's temperature variations appear suspiciously pixel-like, as if the universe's oldest light carries the graininess of a low-resolution hologram. Some theorists argue this could reflect the fundamental bit size of spacetime's underlying code. Others point to anomalies in high-energy particle collisions, where certain scattering patterns match holographic predictions. Even the way quantum entanglement links particles across vast distances, a phenomenon Einstein called spooky action at a distance, fits neatly with holography's idea that separations in 3D space are illusions. The implications are staggering. If the holographic principle holds, the first light wasn't just a physical phenomenon. It was information made visible, a message from the universe's underlying code. Those primordial photons might not have traveled across space at all, but rendered into existence as our cosmic simulation updated its state. And if we're living in a hologram, the glow of the Big Bang isn't a relic. It's the first frame of a projection still playing out, with every star and galaxy just pixels in the grandest display imaginable. Yet mysteries linger. If light is projected from the universe's boundary, where is that boundary? Could we ever detect its presence, or are we trapped inside the illusion? And if the holographic principle is true, what or who is running the simulation? The answers might rewrite not just the history of light, but the nature of existence itself. For now, the theory remains a beautiful, bewildering possibility, one that turns the cosmos into the ultimate magic trick, where even the first dawn was just sleight of hand. Now imagine our universe isn't alone, that it's just one bubble floating in a vast cosmic foam, bumping into other universes with entirely different laws of physics. This isn't just wild speculation, it's the multiverse theory, and some scientists believe these collisions could have sparked the very first light in our cosmos. Picture two soap bubbles drifting toward each other when they touch. the energy released at their boundary might ripple outward in a flash of radiation. Now scale that up to universes. If our infant cosmos collided with another, the sheer force of that impact could have lit up the darkness like a match struck in a void. The math behind this idea is surprisingly elegant. In some versions of string theory, universes form as bubbles in a higher dimensional space, each with its own unique physics. When two bubbles collide, the energy at their intersection doesn't just vanish, it has to go somewhere. Calculations show that even a gentle brush between universes could unleash enough energy to ionize vast regions of space, flooding them with photons. The light wouldn't come from stars or plasma. It would be a cosmic aftershock, a relic of realities slamming together in dimensions beyond our perception. But here's where it gets even stranger. This light wouldn't be uniform. Just as a pebble dropped in a pond creates ripples, a universe collision would leave distinct patterns in the radiation, perhaps even a telltale bruise in the cosmic microwave background. Some researchers argue that certain anomalies in the CMB, like the infamous cold spot, could be scars from such an encounter. Others suggest these collisions might have set off cascading events, triggering the formation of the first galaxies by compressing gas in uneven waves. The implications are staggering. If true, the first light we see might not be from our universe at all. It could be borrowed from another, a flashbulb moment frozen in time from a reality we'll never fully understand. And if bubbles keep colliding in the multiverse, our night sky might still hold echoes of those impacts, remnants of cosmic border crossings written in photons. Of course, skeptics question how we'd ever prove this. Without a way to observe other universes directly, the evidence remains circumstantial at best. Yet the hunt is on. Advanced telescopes are scanning the cosmos for subtle, unexplained patterns in light distribution, while theorists model how different collision scenarios would imprint on the universe's structure. Some even propose that gravitational wave detectors might one day catch vibrations from ancient impacts, like tuning forks humming with the memory of a long-ago crash. What's haunting is the possibility that light itself, the very thing that lets us see the cosmos, might be a foreigner, a refugee from a reality where the rules of physics are utterly alien. The universe's dawn could have been sparked not by internal processes, but by a fleeting touch from somewhere else. And if collisions like this still happen beyond our view, the night sky might someday light up again with echoes from a neighbor we never knew existed. Deep in the cosmic dark ages, when most of the universe still lay shrouded in hydrogen fog, monstrous beacons flickered on, blazing so fiercely they outshone entire galaxies. These were the first quasars, the universe's ultimate lighthouses, powered by ravenous supermassive black holes feasting on gas at the centers of nascent galaxies. Unlike the steady glow of stars or the diffuse afterglow of the Big Bang, quasars were cosmic blowtorches, jets of energy screaming across the void, punching through the darkness that had reigned for millions of years. How did these titans form so quickly after the Big Bang? The answer lies in a perfect storm of conditions. In the early universe, dense knots of dark matter pulled in vast clouds of hydrogen, compressing them until gravity's grip became inescapable. At the core of these collapsing gas giants, black holes sprouted, not the modest stellar mass ones we see today, but seeds weighing thousands of suns born from the direct collapse of primordial gas. Fed by the surrounding chaos, these black holes gorged themselves, spinning up disks of superheated plasma that glowed with the energy of 1 trillion stars. The light they emitted wasn't just visible, it spanned the spectrum from radio waves to gamma rays, a full cosmic orchestra of radiation. What made quasars revolutionary was their reach. Their ultraviolet beams ionized hydrogen for light years around, carving transparent bubbles in the opaque cosmic fog. This wasn't just illumination, it was a transformative force, reshaping the very medium through which light traveled. Some astrophysicists argue quasars didn't just break the dark ages, they accelerated the universe's transition to transparency, acting as cosmic defibrillators that jump-started the era of galaxies. Clues to their impact are etched in the most distant objects we found. The quasar Euler's J1342, for instance, blazed when the universe was just 700 million years old, yet its central black hole already weighed 2 billion suns. Such staggering growth implies these objects were swallowing gas at rates we've never witnessed since. Even more telling are the shadows they cast. Absorption lines in quasar light reveal patches of ionized hydrogen stretching billions of light years, like breadcrumbs marking their influence across epochs. Yet mysteries abound. How did gas flow so efficiently to feed these monsters? Could magnetic fields have funneled matter like cosmic conveyor belts? And why did quasars fade as the universe aged? Their golden age lasted barely a billion years before dwindling, leaving modern galaxies with quieter black holes at their cores. The answer might lie in their violent demise. Perhaps they blew away their own fuel supplies with radiation pressure, or maybe the universe simply ran out of the dense gas clouds they needed to thrive. What's undeniable is their legacy. The light from those first quasars didn't just travel, it engineered the cosmos. By stripping electrons from atoms, they set the stage for modern galaxy formation. Their energy seeded the cosmic web we see today, and their deaths may have enriched space with the heavy elements needed for planets and life. In the grand story of light's origins, quasars were the universe's first great disruptors, proof that darkness never stood a chance against such brilliance. Imagine the early universe threaded with invisible lines of magnetic force, twisting and braiding like cosmic spaghetti in a boiling pot. These weren't the orderly fields we see around stars today. They were chaotic, writhing structures stretched across light years, storing unimaginable energy in their bends and kinks. And when those lines snapped and reconnected, the energy released didn't just vanish. It erupted in bursts of light so intense they could outshine entire galaxies. This is magnetic reconnection, a process we've seen in solar flares and auroras, but scaled up to cosmic proportions in the universe's infancy. The mechanics are deceptively simple. Picture two magnetic field lines running parallel like taut ropes. If they're pushed close enough, they can suddenly rupture and fuse in a new configuration, releasing the tension between them in an explosive flash. On Earth, this process powers the northern lights and solar storms. But in the early universe, where magnetic fields were far stronger and filled vast regions of space, reconnection could have unleashed torrents of radiation, flooding the cosmos with light long before stars turned on. Some models suggest these events might have been so frequent that their combined glow rivaled the cosmic microwave background itself. What made these bursts special was their ability to transform their surroundings. The energy released wasn't just light. It was a mix of X-rays, gamma rays, and high-speed particles, all capable of ionizing hydrogen gas. Unlike the steady glow of recombination or the localized fury of quasars, reconnection was a universal phenomenon, popping off like firecrackers across the darkness. Each flash carved out pockets of transparency, allowing light to travel farther than ever before. It's like poking holes in a blackout curtain. Eventually, enough holes let the daylight pour through. Evidence for this theory hides in the unevenness of the cosmic microwave background. Some of its faint temperature variations could be scars from ancient reconnection events frozen in time. There's also the puzzle of how the universe became so uniformly ionized so quickly. Stars and quasars alone might not have had enough time or reach. But if magnetic reconnection was rampant, it could have supercharged the process, turning the cosmos transparent in fits and starts rather than a slow crawl. The implications are profound. If magnetic fields lit up the early universe, they weren't just passive features, they were active players, shaping the environment where the first galaxies would later form. Their remnants might still linger today, woven into the fabric of galaxy clusters or humming in the voids between them. And if we're right, the universe's first light wasn't just a single dawn. It was a strobe light flickering in the dark, each pulse rewriting the rules of what came next. Yet mysteries endure. How did those primordial magnetic fields form in the first place? Were they born in the Big Bang's chaos or spun up by the motion of early plasma? And could their echoes still be detected in the polarized light of distant galaxies? What's clear is that magnetism's role in cosmic evolution might be far greater than we ever imagined, not just guiding stars and planets, but perhaps igniting the very first sparks in the darkness. In the shadowy realm of theoretical physics, where particles flicker in and out of mathematical existence, there might lurk a ghostly heavyweight, the gravitino. This hypothetical particle is the supersymmetric twin of the graviton, the presumed carrier of gravity, and if it exists, it could rewrite the story of the universe's first light. Picture a particle so massive it bends spacetime just by existing, yet so elusive it slips through detectors unnoticed. Now imagine these cosmic titans dying by the trillions in the early universe, each one vanishing in a burst of energy so brilliant it could have illuminated the cosmos before stars ever formed. The gravitino's story starts with supersymmetry, a theory proposing every known particle has a heavier superpartner with different quantum properties. Gravitinos would be the superpartners of gravitons, threading space with invisible gravitational webs. But here's the twist: in the ultra-dense early universe, gravitinos might have been unstable. Packed too close together, vibrating with too much energy, they could have decayed into lighter particles, including photons. This wouldn't have been a gentle fade out. Calculations suggest each decay could have unleashed high-energy gamma rays, stitching the darkness with piercing beams of light. What makes this idea so tantalizing is the timing. Gravitino decays wouldn't have waited for the universe to cool into atoms. They could have lit up the cosmos during its first terrifying seconds, when temperatures exceeded 1 billion degrees and matter was a churning plasma. Unlike the steady glow of recombination or the localized violence of quasars, this light would have been universal, a shimmering curtain of radiation draped across the entire infant universe. Some theorists argue this could explain certain anomalies in the cosmic microwave background, mysterious fluctuations that don't quite fit standard models of cosmic evolution. Yet proving gravitinos exist is a monumental challenge. These particles would interact with ordinary matter roughly once per galaxy per century, making them nearly impossible to catch. Particle colliders like the Large Hadron Collider hunt for their fingerprints in high-energy collisions, while astronomers scour the cosmos for unexplained gamma-ray bursts that might be their final farewells. Even if we never detect them directly, their legacy could be written in the oldest light we see: photons born not from fire or plasma, but from the death throes of gravity's shadowy twin. The irony is delicious. Gravity, the force we associate with pulling things together, with darkness and collapse, might have played a role in creating light itself. If gravitinos truly decayed into photons, then the first glimmers in the void weren't just a product of heat or collisions. They were the universe translating the language of gravity into the language of light, a cosmic Rosetta Stone written in gamma rays. And somewhere in the depths of space, their descendants might still travel, carrying echoes of that primordial transformation. Imagine our universe as just one page in an infinite cosmic book, floating alongside countless others in a higher dimensional space we can't perceive. This is the heart of the ekpyrotic theory, a radical idea suggesting our cosmos wasn't born from a single Big Bang, but from a catastrophic collision between two of these multidimensional sheets called brains. And when they smashed together, the energy released might have ignited not just matter, but the very first light in existence. The story starts with string theory's boldest claim, that reality isn't just 3 dimensions of space and 1 of time, but 10 or 11 dimensions curled up beyond our perception. In this framework, our entire universe could be a 3-dimensional brain drifting through higher dimensional space like a leaf on a pond. The ekpyrotic model takes this further, proposing that another brain once floated parallel to ours, separated by a gap thinner than an atom. Over eons, gravity drew them closer until crash. The collision didn't destroy the brains, it energized them, flooding our newborn universe with heat, matter, and radiation. That moment of impact, that could have been the match that lit the cosmic candle. What's fascinating is how differently light emerges in this scenario compared to standard Big Bang models. Instead of photons breaking free during recombination, light might have been generated continuously as the brains scraped past each other, like flint striking steel in slow motion. The resulting glow wouldn't be perfectly uniform. Either wrinkles in the colliding brains could have created hotter and cooler patches, explaining the temperature variations we now see in the cosmic microwave background. Some calculations even suggest this process could produce distinct polarization patterns in the CMB, a smoking gun physicists are actively hunting for. The implications rewrite cosmic history. If the ekpyrotic model holds, the Big Bang wasn't a singular beginning, just the latest chapter in an endless cycle of collisions. Each time the brains meet, they reset the universe, erasing old structures but preserving subtle quantum information that shapes the next cycle. Light from prior collisions would have been wiped out, making our current cosmic microwave background not the first light, but simply the most recent. It's a humbling thought. Every star we see might owe its existence to a collision in some hidden dimension, a shadow of events beyond space and time as we know them. Skeptics raise valid questions. Without direct evidence of extra dimensions or brain collisions, how do we test this? Some point to anomalies in the CMB's large-scale structure that don't quite fit inflation theory. Others suggest future gravitational wave detectors might catch echoes of the collision, like ripples from a stone thrown long ago. What's undeniable is the theory's bold vision, that light's origins might lie not within our universe but outside it, in realms where the very fabric of reality is stranger than we dare imagine. Perhaps most poetic is the idea that illumination isn't unique to our cosmic era. If the cycle continues, some future version of the universe will have its own first light, sparked when the brains meet again in a dance older than time. And somewhere, in some dimension we'll never see, another civilization might one day gaze at their night sky, wondering about the collision that started it all, just as we do now. Among the darkness of the early universe, the first stars weren't just born, they died in spectacular fashion, and their deaths may have been the defining moment that truly lit up the cosmos. These weren't the quiet fades of modern stars, they were cataclysmic explosions, violent enough to outshine entire galaxies for weeks. When those first supernovae erupted, they didn't just vanish, they rewrote the rules of the universe, flooding space with light and sprinkling it with the very ingredients needed for planets, life, and everything we know. The stage was set by the first generation of stars, monstrous giants hundreds of times heavier than our Sun. Their immense size meant their cores burned at unimaginable temperatures, fusing hydrogen into helium at a breakneck pace. But this came at a cost. Within just a few million years, a blink in cosmic time, they exhausted their fuel. Without the stabilizing pressure of nuclear fusion, gravity took over, collapsing the star's core in a fraction of a second. The shockwave from that collapse rebounded outward with enough force to tear the entire star apart, triggering a supernova so powerful it would have been visible across the observable universe. The light from these explosions was unlike anything since. Modern supernovae shine brightly, but their light is diluted by dust and gas. In the pristine early cosmos, there was nothing to absorb or scatter the radiation, just pure, unfiltered brilliance. For weeks or even months, each explosion would have blazed with the intensity of 100 billion suns, a temporary beacon in the endless dark. But more importantly, that light wasn't just energy, it carried information. The ultraviolet and X-ray photons from these blasts ripped electrons from surrounding hydrogen atoms, ionizing vast bubbles of gas and clearing the way for light to travel farther than ever before. Yet light was just the beginning. The true legacy of these supernovae was what they left behind. In their cores, the first stars had forged elements heavier than hydrogen and helium, carbon, oxygen, silicon, even traces of gold and uranium. When they exploded, those elements were flung into space at nearly the speed of light, seeding the cosmos with the raw materials for rocky planets, organic molecules, and eventually life itself. We see echoes of this today in the oldest stars, which contain traces of these heavy elements despite forming before most of the universe's chemistry existed. But the story doesn't end with a single explosion. Some of these first supernovae might have been so powerful they triggered chain reactions, their shock waves compressing nearby gas clouds until new stars ignited. Others may have left behind black holes that later grew into the supermassive monsters powering quasars, and a few might have been a rare type called pair instability supernova, so violent they left no remnant at all, vanishing in a blaze of light and antimatter that completely vaporized them. What's astonishing is how much hinged on these brief, violent events. Without them, the universe would have remained a sterile sea of hydrogen and helium. There'd be no planets, no chemistry, no life. Even the cosmic microwave background might look different, its tiny fluctuations shaped by the energy these blasts injected into the cosmos. The first supernova weren't just deaths, they were the universe's first great act of creation, proving that sometimes destruction is the only way to make something new. And if we listen closely, we might still hear their echoes. Some astronomers believe that faint, unexplained gamma-ray flashes in deep space could be the last whispers of those ancient explosions, their light stretched and dimmed by billions of years of cosmic expansion. Others hunt for the chemical fingerprints of the first supernova in the atmospheres of the oldest stars, searching for elements that could only have come from such titanic blasts. Every answer pulls us closer to understanding how darkness gave way to light, not with a whimper, but with the brightest explosions the universe has ever known. Hidden in the equations of quantum physics lies a puzzle so stubborn it's haunted scientists for decades: the strong CP problem, a quirk of nature where certain subatomic interactions defy expectations. To solve it, physicists dreamed up the action, a ghostly particle so light it barely interacts with matter. But here's where it gets cosmic. If actions exist, they might not just be silent spectators in the universe. Under the right conditions, they could transform into photons, shimmering into existence as the universe's first light. This alchemy hinges on a phenomenon called the Primarkov effect. Picture an axion drifting through a magnetic field, perhaps one woven through the early universe's seething plasma. As it passes, the field's invisible force could coax the axion to shed its disguise, morphing into a photon mid-flight. It's like a cosmic shape-shifter, trading its elusive form for a particle of light. In the dense, magnetized chaos of the infant cosmos, this process might have happened countless times, filling space with a faint, omnipresent glow. The timing couldn't be more intriguing. Axions, if they're real, would have been incredibly abundant just after the Big Bang, outnumbering protons by staggering margins. As the universe cooled, their collective decay into photons could have outshone even the cosmic microwave background for brief, blazing moments. Unlike the steady glow of recombination, this light would have flickered unevenly, tied to the tangled magnetic fields threading the early plasma. Some simulations suggest these photons might have carried a unique polarization pattern, a twist in their orientation that telescopes could still detect today. Hunting for this signal isn't just theoretical. Deep in abandoned mines and shielded labs, experiments like ADMX and Haystack are listening for axions converting to microwaves in powerful magnetic chambers. Others scour the cosmic microwave background for anomalies, subtle swirls in polarization that don't fit conventional models. There's even a chance that mysterious X-ray emissions from distant galaxy clusters could be axions decaying in the grip of black hole magnetic fields. What's poetic is how this ties the universe's largest and smallest scales together. A particle invented to solve a subatomic riddle might hold the key to cosmic illumination. If axions did birth light, they'd be cosmic dual citizens, both architects of quantum symmetry and silent midwives to the first dawn. And if we ever catch one in a detector, we won't just be solving a physics puzzle. We'll be glimpsing a process that once turned the void into a canvas of light. Black holes aren't just cosmic vacuum cleaners, they're some of the universe's most brilliant light factories. And in the early cosmos, before stars dominated the scene, these gravitational monsters might have been the primary beacons cutting through the darkness. The secret lies in what happens to matter just before it crosses the point of no return. As gas, dust, and even entire stars spiral toward a black hole's event horizon, they don't just vanish quietly. They form a seething, superheated disk called an accretion disk, where temperatures soar to millions of degrees and friction twists magnetic fields into cosmic particle accelerators. The result, a light show so intense it could outshine galaxies. In the infant universe, conditions were perfect for this process to run wild. Without much competition from stars, early black holes, some just a few decades old, gorged themselves on the dense hydrogen fog left over from the Big Bang. As gas rushed inward, collisions between particles in the accretion disk released torrents of X-rays and gamma rays, flooding surrounding space with high-energy photons. Unlike starlight, which emits across a broad spectrum, this radiation was concentrated and piercing, capable of ionizing hydrogen atoms far beyond the black hole's immediate vicinity. Think of it as a celestial blowtorch burning holes in the cosmic fog and carving out transparent bubbles where light could travel freely. What's fascinating is how efficient this process could have been. Modern supermassive black holes, like the one at the center of our Milky Way, are relatively sedate diners starved of nearby gas. They glow faintly in comparison to their ancient counterparts. But simulations of the early universe show that black holes back then could have been thousands of times brighter, their accretion disks stretching across distances comparable to our solar system. Some of these disks might have even developed jets, narrow beams of particles shot out at nearly the speed of light, emitting focused radiation that could punch through the densest gas clouds like a lighthouse beam through stormy skies. Evidence for this theory hides in the most distant quasars we've observed. These objects, powered by supermassive black holes billions of times the Sun's mass, already existed when the universe was less than 1 billion years old. Their incredible brightness suggests their black hole engines were running full throttle, feasting on primordial gas with unmatched ferocity. And while quasars themselves are rare, smaller black holes, those just a few hundred solar masses might have been everywhere, each contributing a faint but steady glow to the cosmic backdrop. Combined, their light could have been enough to kick-start the end of the Dark Ages, turning the universe from opaque to transparent, one ionized bubble at a time. The legacy of this process might still be visible today. Astronomers have detected puzzling patches of excess X-ray radiation in deep space, with no obvious sources like galaxies or quasars nearby. One explanation, the faded afterglow of countless small black holes that shone brilliantly in the early universe, their accretion disks long since depleted but their light still traveling across the eons. There's even a chance that some of the cosmic microwave background's subtle irregularities were shaped by these ancient powerhouses, their radiation nudging matter into patterns that later became galaxies. Yet mysteries linger. How did black holes grow so massive so quickly? Were they born large from collapsing gas clouds, or did they snowball by merging with one another? And if they were such efficient light producers, why didn't they ionize the entire universe faster? Answers might lie in the delicate balance between feast and famine periods where black holes gorged on gas and shone brightly, followed by quieter eras when they starved and dimmed. Like a campfire flickering in the wind, their light may have come in waves, each pulse pushing the cosmos closer to the era of stars and galaxies. What's undeniable is how this flips our view of black holes. We often think of them as darkness incarnate, but in their youth, they might have been the universe's great illuminators. Their violent, radiant feasts didn't just light up the cosmos, they helped shape it, proving that sometimes the brightest sparks come from the deepest shadows. Dark matter has always played the cosmic role of an invisible puppeteer, shaping galaxies with its gravity while stubbornly refusing to interact with light. But there's a twist in this shadowy tale. Among the leading candidates for dark matter are WIMP weakly interacting massive particles, and their very name hints at their paradoxical nature. While they barely touch ordinary matter, they might have once been the universe's most prolific light makers, their violent collisions igniting the cosmos long before stars took the stage. Picture this: in the universe's first moments, space was so densely packed that WIMP, despite their aloof nature, couldn't avoid bumping into one another. And when they did, something extraordinary happened. According to leading theories, WIMP are their own antimatter counterparts. So when two collided, they didn't just bounce off each other, they annihilated in a flash of pure energy, converting their mass into gamma rays, X-rays, or even visible light. It's like striking cosmic matches in the dark, each collision a momentary flare in the primordial blackness. The math behind this is mesmerizing. If WIMP weigh between 100 and 1,000 times more than a proton, as many models suggest, their annihilation would have unleashed enough energy to outshine the early universe's other light sources combined, at least temporarily. These photons wouldn't have been the gentle glow we associate with stars. They'd have been searing bursts of high-energy radiation, powerful enough to ionize hydrogen and carve bubbles of transparency in the opaque cosmic fog. Some simulations suggest this process could have jump-started reionization, the epoch when the universe became permanently transparent to light. But here's where the plot thickens. Unlike starlight or the cosmic microwave background, WIMP annihilation wouldn't have been evenly distributed. Dark matter clumps into dense filaments and halos, meaning these particle collisions would have been far more frequent in certain regions, perhaps along the invisible scaffolding where galaxies would later form. That unevenness might explain puzzling patches in the cosmic infrared background, faint glows that don't quite align with known light sources. There's even speculation that some of the universe's most energetic gamma-ray bursts could be the last echoes of ancient WIMP annihilations, their light stretched and dimmed over billions of years. The hunt for proof is underway. Deep underground, experiments like Xeno, NNT, and LZ are listening for the rare ping of a WIMP bumping into an atomic nucleus. In space, telescopes like Fermi scour the sky for unexplained gamma-ray signatures that match predictions of dark matter decay. And when the Vera Rubin Observatory comes online, its ultra-sensitive scans might reveal stars moving in ways that only make sense if they're tugged by clumps of annihilating WIMP. What's haunting is the irony. Dark matter, the universe's great obscurer, might have also been its first illuminator. If WIMP are real, their self-destructive tendencies didn't just light up the cosmos, they may have set the stage for everything that followed. Every galaxy, every star, every flicker of light we see today could owe a debt to particles so shy, we've yet to catch them in the act, and somewhere in the darkness, their descendants might still be colliding, unseen, their silent fireworks fading into the void. Among the invisible relics of the Big Bang, alongside the famous cosmic microwave background, flows an even more elusive echo, the cosmic neutrino background. These ghostly particles outnumber atoms by billions to one, streaming through you right now at nearly the speed of light without a single collision. But in the universe's first seconds, these neutrinos weren't just passive spectators. Their subtle gravitational nudges might have shaped where and how the first light emerged. When the universe was just 1 second old, neutrinos decoupled from matter, flying free as the cosmos became too diffused to stop them. This happened long before photons broke free during recombination, meaning these neutrinos were the first particles to travel unimpeded through space. Though individually weak, their collective gravity sculpted the primordial plasma, subtly concentrating matter in some regions while leaving others sparse. These density variations became the cosmic seeds for everything that followed, including where light would eventually shine brightest. Here's the twist: neutrinos didn't just influence structure formation, they might have kick-started light production itself. In regions where neutrinos helped cluster matter, gas collapsed earlier and hotter, forming the first stars and black holes that then flooded space with radiation. Their gravitational fingerprints could explain why some patches of the cosmic microwave background glow slightly brighter neutrino-dense areas where light later escaped more easily. There's even a wild possibility that neutrino interactions with hypothetical sterile neutrinos generated faint photon bursts, adding to the universe's growing glow. The hunt for this neutrino background is one of cosmology's grand challenges. Unlike photons, neutrinos from the Big Bang lack the energy to trigger modern detectors. Yet their imprint lingers in the universe's large-scale structure, the intricate cosmic web of galaxies and voids that mirrors their ancient gravitational blueprint. Future experiments like Ptolemy aim to catch these relic neutrinos directly, while telescopes chart their indirect influence in the clustering of distant quasars. What's poetic is how these weakest of particles might have orchestrated cosmic dawn. While photons get all the glory for ending the dark ages, neutrinos could have been the unseen conductors, arranging the universe's matter so light would eventually shine where and when it mattered most. Their story reminds us that in cosmology, even the faintest actors can cast the longest shadows. For billions of years after the Big Bang, the universe flickered with isolated stars and black holes, bright beacons in the darkness but scattered and alone. Then came the cosmic turning point when these solitary lights began gathering into something far grander, the first galaxies. These weren't just random clusters of stars, they were gravity's masterpieces, pulling together matter, energy, and light on scales never before seen. The birth of galaxies didn't just add more stars to the sky, it transformed how light shaped the cosmos forever. Picture the process like this. As dark matter's invisible scaffolding grew more intricate, it drew ordinary gas into vast swirling pools. Within these pools, the first generation of stars, those massive, short-lived titans, ignited in dense clusters rather than isolation. Their combined ultraviolet radiation became a powerhouse, punching through the surrounding hydrogen fog like sunlight breaking through storm clouds. But here's what changed everything: proximity. Packed together in these fledgling galaxies, stars could ionize gas far more efficiently than lone stars ever could. Their light overlapped and amplified, creating expanding bubbles of transparency where radiation could travel freely across thousands of light years. The scale of this illumination was unprecedented. Early galaxies like GNZ 11, observed as it was just 400 million years after the Big Bang, already blazed with the light of a billion suns. Unlike quasars, brilliant but point-like galaxies were sprawling light factories, their stars working in concert to flood the cosmos with photons. And crucially, their starlight wasn't just raw energy. It carried the signatures of heavier elements forged in stellar cores, painting the universe with new colors beyond the blues and whites of primordial hydrogen fusion. Yet galaxies didn't just emit light, they sculpted its flow. Their gravity bent spacetime itself, acting as lenses that magnified and distorted light from objects behind them. This created some of the earliest cosmic echoes, where multiple images of the same star or galaxy appeared in the sky, a phenomenon we now use to peer even further back in time. Meanwhile, the supermassive black holes at their centers, often the seeds around which galaxies formed, generated jets and accretion disks that added high-energy X-rays and gamma rays to the mix, further ionizing intergalactic space. The consequences rippled across epochs. Regions rich in early galaxies became fully ionized faster, creating uneven bubbles of transparency that astronomers now detect in the fluctuating ionization levels of ancient gas clouds. These galaxies also began the cosmic recycling process. Their supernova and stellar winds blew heavy elements into intergalactic space, enriching future generations of stars with the ingredients for planets and life. The light we see from modern galaxies like Andromeda or the Milky Way carries traces of this legacy photons that have traveled through eons of space, shaped by the very first galactic pioneers. What's astonishing is how quickly this transformation occurred. Within a few 100 million years, barely 2% of the universe's current age galaxies went from non-existent to dominant players in cosmic evolution. Their collective starlight didn't just end the Dark Ages, it built the infrastructure for everything that followed, proving that in the cosmos there's strength and brilliance in numbers. The hunt for these pioneer galaxies continues to push telescope technology to its limits, with JWST spotting galaxy candidates that existed when the universe was less than 300 million years old. We're glimpsing the epoch when light truly went from a flicker to a flood. Each discovery peels back another layer of the mystery, revealing how the universe learned to shine not just with stars, but with the magnificent architectures that bound them together. Among the menagerie of hypothetical particles predicted by supersymmetry, the photino stands out as a ghostly counterpart to the humble photon, a shadowy twin with mass, gravity, and the uncanny ability to vanish into darkness. But in the early universe, these elusive particles might have played a surprisingly luminous role. According to one daring theory, photinos, the superpartners of photons, could have decayed in a spectacular burst of energy, flooding the cosmos with light before stars ever formed. Imagine a particle that carries the essence of light itself but hides in the shadows. Photinos, if they exist, would be invisible to our detectors, barely interacting with ordinary matter. Yet in the extreme density of the primordial cosmos, they might have been anything but quiet. Supersymmetry suggests that every known particle has a heavier partner, and for photons, that partner would be the photino, a fermion with just a whisper of the photon's electromagnetic charm. But here's the twist: under the right conditions, photinos could decay back into their more familiar counterparts, converting their mass into pure, radiant energy. The mechanics are deceptively elegant. In the early universe's seething plasma, photinos would have been born in high-energy collisions, only to decay microseconds later into photons and other light particles. Each decay would have been a miniature fireworks display, a flash of energy released as the photino shed its mass. Multiply this by the trillions upon trillions of photinos that might have swarmed the early cosmos, and you have a potential deluge of light illuminating the darkness from within. Unlike the steady glow of recombination or the localized brilliance of quasars, photino decay would have been a universal phenomenon, flickering like fireflies across the entire infant universe. What makes this theory so captivating is its testability. If photinos decayed into photons, they'd leave a distinct fingerprint in the cosmic microwave background, unexpected spikes in certain frequencies or peculiar polarization patterns that don't align with standard models. Some researchers have even proposed that faint, unexplained X-ray emissions from galaxy clusters could be the lingering echoes of these decays, photons stretched and dimmed by billions of years of cosmic expansion. Experiments like the Alpha Magnetic Spectrometer on the International Space Station are quietly scanning the heavens for just such anomalies, hunting for the spectral whispers of photinos long gone. Yet the implications go beyond mere light production. Photino decays could have subtly altered the balance of matter and radiation in the early universe, tweaking the rate at which galaxies formed. Their gravitational influence, slight but pervasive, might explain why certain regions of space seem to clump together more than our models predict. And if photinos were unstable enough to decay en masse, their absence today would solve another puzzle. why we haven't yet detected dark matter directly despite its overwhelming gravitational presence. The irony is poetic. A particle born from light's shadow, designed by theory to balance the quantum scales, might have been the very spark that ended the cosmic dark ages. If photinos truly decayed into photons, then the first light we see, the glow of the cosmic microwave background, the distant flicker of the earliest stars, could carry traces of their farewell. Every photon might be heir to a hidden lineage, a descendant of particles we've yet to prove exist. Of course, mysteries remain. Why would photinos decay at all when other supersymmetric particles might have lingered? Did they leave behind any stable relics, or did they vanish completely, their only legacy written in light? And if we do find their fingerprints in the cosmos, what other secrets might supersymmetry hold about the universe's dawn? For now, the photino remains a ghost in the equations, but one that, if real, could rewrite the story of how darkness first gave way to light. What if the universe's first light didn't come from our familiar three dimensions at all? Hidden within the equations of theoretical physics lies a mind-bending possibility that extra dimensions, curled up smaller than an atom, could have birthed their own exotic particles, including a shadowy cousin of light called the Kaluza-Klein photon. These higher dimensional travelers might have flickered into existence in the early cosmos, leaving behind echoes of their presence in the oldest light we see today. The story begins with a revolutionary idea from the early 20th century. Physicists Theodore Kaluza and Oskar Klein proposed that gravity and electromagnetism could be unified if our universe had an unseen fourth spatial dimension, a tiny, coiled loop attached to every point in space. Though the math worked, the idea languished until string theory revived it, suggesting not just one but 7 hidden dimensions. In this framework, particles like photons could vibrate in these extra dimensions, creating towers of heavier counterparts with identical properties but different masses, so-called Kaluza-Klein particles. Here's where it gets cosmic. In the searing heat of the early universe, these extra-dimensional photons might have been abundant. Unlike ordinary light, which travels freely through our three-dimensional space, Kaluza-Klein photons would have carried energy from the hidden dimensions into our own as they decayed or interacted. Each transition could have released bursts of radiation, contributing to the primordial glow. Imagine it like ripples in a pond. If some of those ripples came from a dimension perpendicular to ours, their energy would still splash into our reality as light. The telltale signature: these particles wouldn't have decayed like ordinary matter. Their extra-dimensional nature would have imprinted unique patterns in the cosmic microwave background, subtle temperature variations or polarization twists that standard models can't explain. Some theorists suggest that certain anomalies in the CMB's large-scale structure, like unexplained cold spots or spiral-shaped polarization patterns, could be the fingerprints of Kaluza-Klein photons fading from higher dimensions into our own. Yet the implications go far beyond light's origin. If Kaluza-Klein particles exist, they might also explain dark matter's gravitational grip without requiring new particles. Their extra-dimensional mass could weave the invisible scaffold holding galaxies together. And if these photons helped ionize the early universe, they'd forge a link between the fabric of spacetime itself and the dawn of illumination, a reminder that light's story might be written in dimensions we've yet to see. The hunt for proof walks a razor's edge. Particle colliders like the Large Hadron Collider search for Kaluza-Klein signatures in high-energy collisions, brief energy spikes that suggest particles disappearing into extra dimensions. Meanwhile, astrophysicists scour quasar spectra for absorption lines that match predicted Kaluza-Klein photon wavelengths. So far, the dimensions remain hidden, but the math keeps the possibility alive. What's mesmerizing is how this reshapes our cosmic perspective. The first light might not have been a purely three-dimensional phenomenon. It could have been a multidimensional whisper leaking into our universe from realms curled tighter than an atom's heart. If true, every photon carries a secret that reality is far roomier than it seems, and the dawn we've been studying was just one slice of a richer, deeper genesis. And somewhere beyond the limits of our perception, those extra dimensions might still vibrate with the echoes of that first light, waiting for us to decode their hidden message. What if the universe's first light wasn't born in our cosmos at all, but in a parallel one, a shadowy twin where particles move backward through time, obeying flipped laws of physics? This isn't science fiction. It's the mirror matter hypothesis, a daring theory proposing that our universe shares space-time with a hidden counterpart, and their fleeting interactions might have sparked the primordial glow we now call the cosmic microwave background. Picture two universes layered atop each other like translucent sheets, identical in structure but fundamentally inverted. In this mirror world, atoms are built from particles with opposite charges and spins, right-handed where ours are left-handed, positive where ours are negative. Normally, these twin realms would never interact, their particles slipping past each other like ghosts. But in the extreme conditions of the Big Bang, when energies reached unfathomable heights, the barrier between them might have briefly thinned. And where they touched, something extraordinary happened. Mirror particles collided with ours in flashes of annihilation, converting their alien mass into bursts of familiar photons. It's as if the universe struck a match against its own reflection, igniting the first light in the process. The implications are staggering. Unlike standard models where light emerges from our universe's cooling plasma, this theory suggests photons could have been forged in the quantum friction between realities. These interactions wouldn't have been random. Mirror matter's unique properties might explain why the cosmic microwave background isn't perfectly uniform. Those tiny temperature variations, they could be scars from where mirror galaxies or black holes brushed against our infant cosmos, leaving behind patches of extra heat as they decayed into light. Some researchers even speculate that certain high-energy gamma-ray bursts with no visible source might be echoes of these collisions, reverberating across dimensions long after the mirror universe faded from view. But how could such a wild idea be tested? The answer lies in neutron stars. These ultra-dense stellar corpses sometimes spin slower than physics predicts, as if something invisible were dragging on them. Mirror matter, with its gravitational pull, could explain this anomaly, and if mirror particles occasionally leak into our world, they might leave faint traces in particle colliders. Experiments like the Large Hadron Collider are already hunting for anomalies in proton collisions that could hint at these elusive interactions. Even more tantalizing are certain isotopes that seem to vanish during decay experiments, as if their particles briefly stepped into the mirror realm before returning. The beauty of this theory lies in its duality. Light, the very thing that lets us see the universe, might owe its existence to forces we can't see, a cosmic handshake between realms that have since drifted apart. And if mirror matter still lingers, woven into the fabric of space, it could solve another mystery: dark matter, those invisible halos surrounding galaxies. They might be the faint gravitational whispers of our universe's mirror twin, forever just out of reach. Yet the biggest question remains: if mirror matter helped birth light, where is that parallel universe now? The answer might lie in the first split second after the Big Bang, when inflation stretched spacetime so violently that the mirror realm was flung beyond any detectable horizon. Like a photograph's negative fading in sunlight, its presence diminished, but not before leaving its mark in the oldest light we know. Every photon carries that history, a secret woven into its quantum fabric, that the dawn we see may be just half of a story written in twin flames. At the very heart of the Big Bang, where temperatures and densities reached unimaginable extremes, there might have been an object so strange it defies our current laws of physics, a Planck star. This theoretical remnant isn't a star in the traditional sense, but rather a quantum knot of spacetime itself, a relic from the moment of creation that could have glowed faintly as it unraveled. Picture a black hole running in reverse instead of collapsing endlessly into a singularity. A Planck star represents the smallest possible volume the universe allows, rebounding outward in a process that might have leaked energy in the form of light during the cosmos's first fragile moments. The concept emerges from loop quantum gravity, a theory attempting to bridge Einstein's relativity with quantum mechanics. Unlike classical black holes that crush matter into an infinitely dense point, a Planck star hits a fundamental limit. The Planck length, about a trillionth of a trillionth the size of a proton, where quantum effects cause spacetime to bounce rather than collapse. This bounce wouldn't be instantaneous. The star could linger in this ultra-compact state for billions of years, evaporating slowly through Hawking radiation. But in the early universe, when the Planck star was fresh and seething with energy, that evaporation might have been far more dramatic, releasing bursts of photons as spacetime itself unraveled at the quantum scale. What makes this idea so compelling is its potential to solve one of cosmology's great paradoxes, the black hole information problem. If black holes truly destroy information, it violates quantum theory's tenet that information can't be lost. A Planck star offers an elegant solution. Information isn't destroyed but preserved in the star's quantum structure, eventually released as the star evaporates. Those final moments of evaporation, they could have been a light show on a cosmic scale, with trillions of Planck stars popping like quantum firecrackers, each contributing photons to the universe's growing glow. The light from these objects wouldn't resemble starlight or the cosmic microwave background. Planck stars would emit energy across the spectrum, from radio waves to gamma rays, with signatures tied to their quantum structure. Some models suggest their radiation could have carried distinct imprints, subtle spikes in certain frequencies or irregularities in the cosmic microwave background's polarization. These fingerprints, if they exist, might still be detectable today, hiding in the noise of ancient light we've already mapped. Of course, challenges remain. Planck stars exist squarely in the realm of quantum gravity, a field without experimental verification. Their lifetimes would depend on their initial mass. Some might still be evaporating now in distant corners of the universe, their faint Hawking radiation lost in the cosmic static. And without direct observation, proving their role in lighting the early cosmos is like reconstructing a fire from its ashes, yet the search continues. Gravitational wave observatories, ever more sensitive, might one day catch the echo of a Planck star's final moments, a tremor in spacetime from an object smaller than an atom but heavier than a mountain. What's poetic is how this theory ties the universe's birth to its potential death. If Planck stars exist, they're cosmic time capsules, preserving the conditions of the Big Bang in their quantum cores. Their light, emitted as they faded, would carry whispers from the very edge of existence, a reminder that even in the darkest objects, illumination finds a way. And if we're right, the universe's first light didn't just come from fire or collision, but from spacetime itself, trembling at the brink of infinity. Before the first stars could ignite, before light could flood the cosmos, the universe needed a cosmic coolant, something to take the edge off the searing heat left by the Big Bang. Enter molecular hydrogen, the unsung hero of cosmic dawn. This simple pairing of two hydrogen atoms might seem unremarkable today, but in the early universe it was the key that unlocked star formation, and with it the universe's first true light. Here's why molecular hydrogen was so revolutionary. In the aftermath of the Big Bang, the universe was filled with hot, ionized gas, mostly single hydrogen atoms buzzing with energy. These atoms were too energetic to clump together under gravity's gentle pull. Without a way to shed that heat, gas clouds couldn't collapse into the dense cores needed to spark nuclear fusion. But molecular hydrogen changed the game. When two hydrogen atoms teamed up, they gained a superpower, the ability to vibrate and rotate, releasing excess energy as infrared radiation. It was like opening a cosmic pressure valve, letting gas clouds cool from thousands of degrees to just a couple hundred, cold enough for gravity to finally take over. The process wasn't quick or easy. Forming molecular hydrogen in the early universe was like trying to build a snowman in a desert. Without dust or heavy elements to help atoms bond, hydrogen molecules had to rely on a fragile three-step dance. First, a free electron latched onto a hydrogen atom, forming a temporary negative ion. Then, another hydrogen atom approached, drawn by the slight charge. Finally, the electron hopped to the newcomer, stitching the two atoms together before darting away. This delicate reaction was 1,000,000 times slower than modern molecular formation, but in the vast, patient expanse of the early cosmos, it was enough to seed change. Once molecular hydrogen took hold, its effects cascaded. Cooled gas pockets began collapsing, their centers growing denser and hotter until ignition. The first protostars flickered to life, their cores still too cool for full nuclear fusion but warm enough to glow faintly in the infrared. These weren't the brilliant beacons we associate with stars today. They were more like cosmic embers smoldering in the darkness. Yet their formation set the stage for the true stellar revolution to come. As more gas cooled and collapsed, these protostars grew, gathering mass until their cores became hot enough to fuse hydrogen in earnest, the moment the first true stars blazed into existence. But molecular hydrogen's role didn't end there. The infrared light emitted by those earliest protostars couldn't travel far through the dense surrounding gas, but it didn't need to. Instead, it pumped energy into nearby hydrogen molecules, exciting them to vibrate even more vigorously. This created a feedback loop. More molecular hydrogen meant more cooling, which led to more star formation, which in turn produced more light to energize even more molecules. The universe was bootstrapping its way out of darkness, one molecular handshake at a time. Evidence for this pivotal era hides in the most distant light we can observe. Quasars from the cosmic dawn show absorption lines indicating vast clouds of molecular hydrogen, ghosts of the cooling gas that birthed the first stars. Simulations of the early universe struggled to form stars without including molecular hydrogen's cooling effects, reinforcing its starring role. And while we can't directly observe those first fragile molecules, their legacy is written in the cosmic structures we see today, the galaxies, clusters, and voids that trace back to those initial cold spots in the primordial gas. What's mesmerizing is how contingent this all was. If hydrogen atoms had been slightly less likely to form molecules, or if their cooling had been slightly less efficient, star formation might have stalled, leaving the universe forever dark. Instead, this simplest of molecules became the universe's first refrigeration system, chilling the chaos just enough for light to emerge. And every star that followed, every galaxy, every planet, every flicker of illumination, owes its existence to those first, fragile partnerships between hydrogen atoms. Yet mysteries linger. Were there other molecules aiding hydrogen in cooling the early universe? Could exotic processes we haven't discovered yet have played a role? And if we could rewind time to witness that epoch, would we see molecular hydrogen forming in predictable patterns or in chaotic, uneven bursts? The answers might reshape our understanding of how the universe transitioned from featureless plasma to a sky ablaze with light. For now, molecular hydrogen stands as a quiet testament to an essential truth. Sometimes the smallest bonds can ignite the greatest transformations. At the quantum level, empty space is never truly empty. It thrums with a hidden energy, a seething ocean of virtual particles flickering in and out of existence. This is the vacuum energy, a background hum woven into the fabric of reality itself. And in the universe's first moments, when conditions were unimaginably extreme, that energy might have done more than just simmer. It could have erupted, unleashing torrents of photons in a flash that lit up the cosmos before stars ever had a chance. Picture the vacuum like a stretched rubber band, tension humming through every inch of space. According to quantum field theory, this energy isn't static. It fluctuates, with tiny regions briefly surging to higher or lower energy states. Normally, these fluctuations cancel each other out, leaving no trace. But in the early universe's ultra-dense environment, something extraordinary might have happened. Regions of false vacuum higher energy pockets trapped like bubbles in supercooled water could have suddenly decayed to a lower energy state, releasing their pent-up energy as radiation. Think of it like popping a cosmic blister, with each rupture flooding the surrounding space with light. The scale of these events defies imagination. A single vacuum decay could have unleashed enough energy to outshine a galaxy, if only for an instant, and because false vacuum pockets would have formed chaotically across the young cosmos, their simultaneous decays might have created a staggeringly uneven light show, patches of brilliant illumination interspersed with regions still shrouded in darkness. This could explain some of the cosmic microwave background's quirks, like unusually hot or cold spots that don't quite fit standard models of the early universe. What's fascinating is how this process differs from other light-producing mechanisms. Unlike starlight, born from nuclear fusion, or the glow of recombination, which emerged as electrons settled into atoms, vacuum energy release would have been a purely quantum phenomenon, light springing directly from the fabric of space itself. There's even a spine-tingling possibility that these decays didn't just produce photons, but also triggered chain reactions, with each energy release nudging nearby regions toward their own tipping points. The result, a cascade of light bursting through the cosmos like fireworks in a darkened sky. Evidence for this theory is elusive but tantalizing. Precise measurements of the cosmic microwave background reveal subtle anomalies slightly over or under dense regions that could be scars from ancient vacuum decays. Particle colliders have glimpsed hints of vacuum-like states in high-energy experiments, fleeting moments where the rules of physics seem to shift. And if we're right, the universe might still harbor pockets of false vacuum today, lurking undetected, waiting to decay and rewrite reality in an instant. The implications ripple far beyond light's origin. If vacuum energy powered the first illumination, it means the universe's dawn wasn't just shaped by matter and radiation, but by the underlying energy of space itself. A reminder that nothing, not even the void, is ever truly at rest. And somewhere in the night sky, those first photons might still travel, carrying whispers of the moment space itself chose to shine. From the unimaginable heat of the Big Bang's afterglow to the eerie decay of shadowy particles, we've explored 30 breathtaking theories about how light first pierced the cosmic darkness. Each one paints a radically different picture of the universe's dawn, whether it was the explosive death of primordial black holes, the quantum flicker of virtual particles, or even a collision with a mirror universe lurking in hidden dimensions. Some theories, like the cosmic microwave background from recombination, are pillars of modern cosmology. Others, like photinos decaying into light or magnetic reconnection sparks, push the boundaries of known physics. What's astonishing isn't just the variety of ideas, it's how each one forces us to rethink what light even means. Was it a byproduct of spacetime's birth, a message from extra dimensions, or the last gasp of invisible dark matter? The beauty of this mystery is that no single answer feels complete. The cosmic microwave background tells one story, but the whispers of population 3 stars suggest another. Gravitino decays and axion transformations hint at forces beyond our current understanding, while ekpyrotic brain collisions propose origins outside our universe entirely. Even the humblest molecules, like hydrogen, might have played a starring role in cooling the cosmos just enough for starlight to ignite. Every theory, whether mainstream or fringe, adds another layer to the puzzle, proving that the universe's first light wasn't just an event, but a symphony of possibilities. So which theory resonates with you? Maybe you're captivated by the elegance of quantum fluctuations stretching into light, Or perhaps you're drawn to the drama of primordial black holes evaporating in a blaze of radiation. Whatever sparks your curiosity, let us know in the comments. We're just getting started unraveling space's greatest mysteries. And if you've enjoyed this journey to the edge of cosmic dawn, don't forget to subscribe. Who knows, the next video might explore the theory that finally lights up the truth. Until then, keep looking up and wondering.